Domain and range. One of our main goals in mathematics is to model the real world with mathematical functions. In doing so, it is important to keep in mind the limitations of those models we create. This table shows a relationship between circumference and height of a tree as it grows. While there is a strong relationship between the two, it would certainly be ridiculous to talk about a tree with a circumference of -3 feet or a height of 3,000 feet. When we identify limitations on the inputs and outputs of a function, we are determining the domain and range of the function. Domain and range. Domain, the set of possible input values to a function. Range, the set of possible output values of a function. Using the tree table above, determine a reasonable domain and range. Example 1. We could combine the data provided within our own experiences and reason to approximate the domain and range of the function h equals f of c. For the domain, possible values for the input circumference c, it doesn't make sense to have negative values, so c greater than 0. We can make an educated guess at a maximum reasonable value or look up that the maximum circumference measured is about 119 feet. With this information, we would say a reasonable domain is 0 less than c less than or equal to 119 feet. Similarly, for the range, it doesn't make sense to have negative heights, and the maximum height of a tree could be looked up to be 379 feet. So a reasonable range is 0 less than h less than or equal to 379 feet. Example 2. When sending a letter through the United States Postal Service, the price depends upon the weight of the letter, as shown in the table below. Determine the domain and range. Suppose we notate weight by W and price by P, and set up a function named P, where price, P, is a function of weight, W. P equals P of W. Since acceptable weights are 3.5 ounces or less and negative weights don't make sense, the domain would be 0 less than W less than or equal to 3.5. Technically, 0 could be included in the domain, but logically, it would mean we are mailing nothing, so it doesn't hurt to leave it out. Since possible prices are from a limited set of values, we can only define the range of this function by listing the possible values. The range is P equals 50 cents, 71 cents, 92 cents, or $1.13. Notation. In the previous examples, we used inequalities to describe the domain and range of the functions. This is one way to describe intervals of input and output values, but is not the only way. Let us take a moment to discuss notation for domain and range. Using inequalities such as 0 less than c less than or equal to 163, 0 less than W less than or equal to 3.5, and 0 less than H less than or equal to 379 imply that we are interested in all values between the low and high values, including the high values in these examples. However, occasionally we are interested in a specific list of numbers like the range for the price to send letters. P equals 44 cents, 61 cents, 78 cents, or 95 cents. These numbers represent a set of specific values. Representing values as a set or giving instructions on how a set is built leads us to another type of notation to describe the domain and range. Suppose we want to describe the values for a variable x that are 10 or greater, but less than 30. In inequalities, we would write 10 less than or equal to x less than 30. When describing domains and range, we sometimes extend this into set builder notation. The curly brackets are read as the set of, and the vertical bar is read as such that. So altogether, we would read the set of x such that 10 less than or equal to x less than 30 as the set of x values such that 10 is less than or equal to x and x is less than 30. So for our tree height example above, we could write for the range the set of h values such that 0 is less than h and h is less than or equal to 379. In set builder notation, if a domain or range is not limited, we could write the set of t values such that t is a real number, or read as the set of t values such that t is an element of the set of real numbers. A more compact alternative to set builder notation is interval notation, in which intervals of values are referred to by the starting and ending values. Curved parentheses are used for strictly less than, and square brackets are used for less than or equal to. Since infinity is not a number, we can't include it in the interval, so we always use curved parentheses with infinity and negative infinity. The table below will help you see how inequalities correspond to set builder notation and interval notation. To combine two intervals together using inequalities or set builder notation, we can use the word or. In interval notation, we use the union symbol to combine two unconnected intervals together. Example 3. Describe the intervals of values shown on the line graph below using set builder and interval notations. To describe the values x that lie in the intervals shown above, we would say x is a real number greater than or equal to 1 and less than or equal to 3, or a real number greater than 5. As an inequality, it is 1 less than or equal to x and x is less than or equal to 3, or x is greater than 5. In set builder notation, the set of x values such that 1 is less than or equal to x and x is less than or equal to 3, or x is greater than 5. Remember, when writing or reading interval notation, using a square bracket means the start value is included in the set. Using a parentheses means the start value is not included in the set. Domain and range from graphs. We can also talk about domain and range based on graphs. Since domain refers to the set of possible input values, the domain of a graph consists of all the input values shown on the graph. Remember that input values are almost always shown along the horizontal axis of the graph. Likewise, since range is the set of possible output values, the range of a graph we can see from possible values along the vertical axis of the graph. Be careful. If the graph continues beyond the window in which we can see the graph, the domain and range might be larger than the values we can see.